So today we are going to see DACs. So binary weighted DAC. DAC stands for digital to analog converters. These are type of data converters where the input is generally a digital number and you get an equivalent analog output signal. So these DACs convert binary or non-binary numbers and codes into analog ones with its output voltage which is proportional to the digital inputs number. For example, you are taking a 4-bit input as binary which ranges from 0000 to 1111. Then the DAC converts it to an output analog voltage ranging from 0 to 10 volts. So this is a block diagram of DAC where the input is digital and the output is analog. There are two types of DAC, weighted resistor DACs and R2R ladder DACs. We are going to see about weighted resistor DAC. So in case of weighted resistor DAC, it is basically binary weighted resistors in an inverter adder circuit. So generally binary weighted resistors are shortly called as weighted resistor DACs. Here you given 3-bit binary input which is in the form like B2, B1 and B0, where B2 is most significant bit and B0 is the least significant bit. This is a circuit diagram which is used where the first half with an op-amp is then inverting adder circuit and you are using resistors here to convert the binary input into an analog signal and thus it is known as weighted resistor DACs. So here the non-inverting input terminal of the op-amp is connected to the ground, which means that 0 volts is applied at non-inverting input terminal. As per the virtual short concept, the voltage at inverting input terminal is same as voltage at non-inverting input terminal. Therefore, it is 0. And moving on, we can start with a nodal equation where we get VR Vf by R into B2 by 2 power 0 plus B1 by 2 power 1 plus B0 by 2 power 2 in whole bracket gives you the V out. Here B2, B1 and B0 is the bits that compile together to give you the binary input given. Here we are substituting R equal to 2 of RF, where RF gets cancelled and in the next equation you get V0 equal to VR by 2 into same B2 by 2 power 0 plus B1 by 2 power 1 plus B0 by 2 power 2. Here this is the output voltage equation for a 3-bit binary weighted resistor DACs. But generally you can have an n number of bits as input. So in that case you have VR by 2 into B of n minus 1 by 2 power 0 plus B of n minus 2 by 2 power 1. And at the end you get B0 by 2 power n minus 1. As you can see, numerator keeps decrementing and denominator gets increasing. This is the whole idea. When you are going to see that summing amplifier in an with the op-amp used as summing amplifier in an enlarged view, you can see we are using here an inverting voltage amplifier where the RF biases the inverting input of the op-amp at 0 potential. So here we are using negative feedback as op-amps usually do. A summing amplifier in inverting mode produces negative sum of any number of input voltages, whereas a non-inverting summing amplifier would produce a positive sum of any number of input voltages. So this is basically how an inverting summing amplifier circuit works. So since we are using an amplifier, an adder circuit as op-amp in our DAC, which is an application. So this is how an op-amp generally works. So these are the normal general equations for finding V out and IF of the op-amp alone. So this op-amp is basically used as an application. We have DAC, that is digital to analog converters. Also in analog to digital converters we can use op-amps.
Four-digit converter. This is the DA converter with binary weight resistors. From this circuit, we can see that the op-amp is connected in the inverting mode, but it can also be connected in the non-inverting mode. Here the number of binary inputs is 4. Therefore the 4-bit converter will have 2 power 4, that is equal to 16 combinations of output. 4 switches from B0 to B3 are available to simulate the binary inputs. In practice, a common example that can be used is 7493, that is, it is a 4-bit binary counter. It can also be used. Now looking into the working of this basically works as a current to voltage converter. Case 1 is when B0 is closed. So when B0 is closed, the voltage across R will be in such way that it is connected directly to the plus 5 volt. So voltage across R will be 5 volt. Current through resistor R will be V by R, that will be 5 volt divided by 10 kilo ohms, that will be 0.5 into 10 power minus 3, 0.5 milliamps. Current through RF, that will be current through the feedback resistor. RF will be 0.5 milliamps. Since input bias current IB is negligible here, we will be taking it as 0.5 milliamps. Output voltage in case 1 will therefore be 1 kilo ohms into 0.5 milliamps in negative, that is equal to minus 0.5 volt in the negative direction. Case 2 is for when B1 is closed and B0 is open. Voltage across resistor R will be 5 volt. Current through R and RF. Current through R will become twice the value of current to flow through RF, and the output voltage therefore it also doubles. In case 3, for B0 and B1 both are kept closed. Here the current flowing through RF will be 1.5 milliamps. Therefore output voltage will be 1 kilo ohm into 1.5 milliamps in the negative direction, so that will be equal to minus 1.5 volt. Inference will be according to this position, that is on or off of the switches, 3 switches B0 to B3, the corresponding binary weighted currents will be obtained in the input resistor. The current through RF will be the sum of these 3 currents. The overall current is then converted to its proportional output voltage. So first the current through will be summed up, and then the overall current is converted to the proportional output voltage. Naturally the output will be the maximum if the switches are all closed, that is V0 is equal to minus RF into B0 by R into B1 by R by 2 to B2 by R by 4 into B3 by R by 8. So where each of the inputs B3, B2, B1, B0, they may be either high and low. The highest voltage is plus 5 volt and the lower voltage is 0 volt. Graph analysis. The graph analysis for the 4-digit converter. The output will be a negative going staircase waveform with 15 steps, each 0.5 volt in the negative. Due to the variations in the logic high voltage levels, all the steps will not have the same size. The feedback resistor value will also be changing as the size of the steps. It changes the size of the steps. Thus, a desired size for a step can be obtained by connecting the appropriate feedback resistor. So if you need a desired size for the step, then we need to be calculative in choosing the best feedback resistor. Only with that we'll be getting a perfect size for the step. The only condition to look out for is that the maximum output voltage should not exceed the saturation levels of the op-amp. Then there will be many other side effects. Metal film resistors are more preferred for obtaining accurate outputs.
Applications of D2A converters. DACs are used in many digital signal processing applications. Let us discuss some of the important applications. The first is the audio amplifier. DACs are used to produce DC voltage gain with microcontroller commands. And also the DACs will be incorporated into an entire audio codec, which includes signal processing features. Video encoder. The video encoder system will process a video signal and send digital signals to a variety of DACs to produce analog video signals of various formats. As with audio codecs, these ICs may have integrated DACs. Display electronics. The graphic controller will typically use a lookup table to generate data signals sent to a video DAC for analog outputs such as RGB signals to drive a display. Data acquisition systems. Data to be measured is digitized by an A to D converter and then sent to a processor. The data acquisition will also include a process control in which the processor sends feedback data to a DAC for converting to analog signals. Calibration. The DAC provides dynamic calibration for gain and voltage offset for accuracy in test and measurement systems. Motor control. Many motor controls require voltage control signals, and a DAC is ideal for this application, which may be driven by a processor or controller. Data distribution system. Many industrial and factory lines require multiple programmable voltage sources, and this can be generated by a bank of DACs that are multiplexed. The use of DAC allows the dynamic change of voltage during operation of a system. Digital potentiometer. Almost all digital potentiometers are based on the string DAC architecture. With some reorganization of the resistors, switch array, and the addition of an 12C compatible interface, a fully digital potentiometer can be implemented. Software radio. A DAC is used with a digital signal processor to convert a signal into an analog for transmission in the mixer circuit and then to the radio power amplifier and transmitter. Advantage of D2A converter. Weighted resistor circuit is the fastest converting circuit compared to other methods. High resolution and accuracy can be achieved. DACs are simple to implement. Disadvantage of DAC. Voltage levels must be exactly the same for all inputs in weighted resistors DAC. Example, 4-bit converter requires 4 resistors. Binary weighted resistor circuit that require op-amps are expensive. Power dissipation of binary weighted resistor circuit is very high. In R2 or later converters, delay is caused as the circuit needs switching based on the inputs. Gain error, offset error, non-linearity is commonly caused by resistors used in the circuit. Thank you.